Hey everyone, and welcome to our deep dive on magnets.
Yeah, magnets.
We're going full physics nerd today and looking at some lecture notes that someone sent in all about magnetism.
Cool.
I think this will be interesting for anyone who's maybe brushing up on their physics knowledge,
That's right.
or just anyone who's ever looked at a magnet and thought how does this actually work?
Yeah.
So get ready to discover the strength of a fridge magnet and what's going on inside those MRI machines and the world of magnetic domains.
That's right.
All that good stuff.
Kind of like magic, right?
Yeah.
Like those little pieces of metal clinging to the fridge.
Yeah.
A compass mysteriously pointing north.
Yeah.
But in reality, it's all rooted in fundamental physics.
Okay.
Specifically, the interactions between electricity and magnetism.
Yeah, the notes start out by really highlighting how interconnected electricity and magnetism are.
Exactly.
Like anytime electrons are moving, they create a magnetic field.
That's what Ørsted observed a long time ago.
Right. And is that what led to formulas to calculate the strength of the magnetic field?
That's right.
Okay.
Yeah. So the notes specifically mention one formula. B equals mu naught. I divided by 2 pi r.
Okay.
Now, don't worry. We won't get bogged down in the math here.
No.
But think of B as the strength of the magnetic field.
Okay.
I is the amount of electric current flowing.
Okay.
R is the distance from the wire.
Got it.
And then mu naught is a constant value.
Okay.
So this formula is essentially telling us how strong the magnetic field will be at a certain distance from a wire, carrying a specific current.
So the notes use this formula, and they calculate the current needed to create a magnetic field as strong as the Earth's magnetic field.
Right.
At a distance of 4 centimeters.
Yep. And it turns out it takes a whopping 10 amps.
Wow.
Which is kind of a lot.
A lot.
When you think about it, because the Earth's magnetic field is actually pretty weak.
Yeah.
Compared to, say, a fridge magnet.
Oh, really?
Yeah.
Okay, I was going to say those fridge magnets are strong.
They are super strong.
But I didn't realize they were that much stronger.
Yeah, the notes say that you need a massive 1,000 amps to match the strength of a fridge magnet.
Wow.
At the same distance.
So I guess that means that just simply moving electrons through a wire isn't always the most efficient way to create a strong magnetic field.
Right, so then how can we amplify that magnetic force?
Yeah, how do we do it?
That's where solenoids come in.
Solenoids?
Yeah.
Okay, I think I remember that word from high school physics.
Yeah, they're pretty cool.
Something about coiled wires.
Exactly. So imagine a wire tightly wound into this helix.
Like a spring.
Yeah, just like a spring. And what this does is it concentrates the magnetic field lines, boosting the overall strength.
Okay.
And the more turns of wire you pack into the solenoid, the stronger the magnetic field gets.
Oh, okay. So that's how they make those super strong magnet, like in an MRI machine.
Yeah, that's right. MRI machines use huge superconducting solenoids to generate these really strong magnetic fields.
Wow. So those superconducting wires are key because they can carry a ton of current.
Yeah, that's right. They have zero resistance.
So they're not losing any energy to heat.
Right.
Which allows for those ultra-strong fields.
Exactly. And have you ever noticed that loud banging you hear during an MRI scan?
Oh, yeah. I do not like that sound.
Yeah, I don't think anybody does. But that's actually caused by these smaller solenoids called gradient coils.
Okay.
And what they do is they're used to shape and fine-tune that main magnetic field.
Oh, interesting.
So by rapidly switching these gradient coils on and off, they create very specific variations in the magnetic field.
Okay.
Which are crucial for capturing those detailed images of your insides.
So there's a lot more to it than I thought.
Oh, yeah.
Okay, well, let's go even smaller now. Let's zoom into individual atoms.
Okay.
The notes mention these things called magnetic dipoles.
Yes.
Which are essentially like tiny magnets at the atomic level.
That's right. So even individual atoms can act like miniature magnets.
Wow.
And that's where things get really interesting.
Okay.
So essentially, a magnetic dipole is a tiny loop of current, like an electron orbiting an atomic nucleus.
Okay.
The notes also have a formula for the magnetic dipole moment.
Okay.
But the key takeaway is that the strength of this tiny atomic magnet depends on the amount of current flowing in that loop and the size of the loop itself.
Okay, so we have these tiny magnets, but they're not just sitting there statically, right?
They're not.
They're not just vibing.
No, they like to align themselves with external magnetic fields.
Oh, really?
Yeah, just like a compass needle aligns itself with the Earth's magnetic field.
Right.
These magnetic dipoles try to do the same thing with any magnetic field they encounter.
And why is that?
It's all about minimizing their potential energy.
Oh.
It's like they're trying to find that most stable configuration.
So is there a way we can kind of visualize this alignment without having to think about all the complex equations?
Yeah, for sure. So think of an electric dipole,
Okay.
which is basically a positive and negative charge separated by a small distance. So if you put this electric dipole in an electric field,
Okay.
it will rotate to align itself with those field lines,
Okay.
with the positive end pointing towards the negative end of the field.
Got it.
And the same principle applies to those magnetic dipoles in a magnetic field.
So those tiny magnets are like miniature compass needles?
That's a great way to think about it.
Always trying to point north.
Yeah, always trying to find that most stable alignment.
So I'm guessing that not all materials respond to magnetic fields the same way, though, right?
You're exactly right.
Okay.
So the notes talk about a few different ways that materials respond. So we've got paramagnetism,
Okay.
dimagnetism,
Okay.
and then the really interesting one, ferromagnetism.
Okay, so break it down for me. What's the difference between all those magnetisms?
All right, so in paramagnetic materials, those tiny atomic magnets, they align slightly with the applied magnetic field.
Okay.
So they're kind of boosting the field strength inside the material just a tiny bit.
So it's a very subtle effect.
Yeah, very subtle.
Okay.
Now, on the other hand, diamagnetic materials,
Uh-huh.
they actually have atomic magnets that oppose the applied field.
Oh, wow.
So they actually make the field inside the material slightly weaker.
Interesting.
So they're kind of pushing back against the magnetic field a little bit.
So I guess this explains why some materials are attracted to magnets.
That's right.
And others are slightly repelled.
Exactly. It all comes down to how those atomic magnets are responding to that external magnetic field.
Okay, that makes a lot more sense.
Good.
But then there's that third one, ferromagnetism.
Right.
What makes that one special?
So ferromagnetism is kind of the magnetism that we're most familiar with in our everyday life.
Okay.
It's what gives us those super strong magnets that we see in everything.
Okay.
From like hard drives to electric motors.
So what makes ferromagnetic materials so much stronger than these other types of magnets?
All right, so there's two key factors here. First, the atoms in ferromagnetic materials have unpaired electrons in their outer shells, which act like super tiny but very powerful magnets.
Gotcha.
And then second, there's this unique quantum mechanical effect that forces neighboring atomic magnets to actually align with each other.
So they're all like holding hands and pointing in the same direction?
Exactly. That's a great way to put it. And so this alignment creates these incredibly strong magnetic fields.
Wow.
Up to 100 or even 1,000 times stronger than that applied field.
That's a huge difference.
It really is.
Yeah.
And this coordinated alignment gives rise to what we call domains.
Domains. So
Yeah.
are those like little magnetic kingdoms inside the material?
Yeah, that's a great analogy.
Okay.
So imagine these microscopic regions within the material
Oh, okay.
where all of the atomic magnets are perfectly aligned, pointing in the same direction.
Mm-hmm.
Each domain acts like a tiny but super strong magnet.
So it's like having billions of tiny magnets all pointing the same way.
That's right.
So then why isn't like a piece of iron just a giant magnet?
That's a great question, and this is where things get even more interesting.
Okay.
So initially, all of these domains are randomly oriented
Okay.
throughout the material.
Okay.
So even though each domain is strongly magnetized, they're all pointing in different directions,
Yeah.
effectively canceling each other out.
Oh, so it's like a room full of people all shouting different directions.
That's a perfect analogy. Yeah.
It's just noise. You can't understand anything.
It's just chaos.
Yeah, exactly.
So like a piece of iron fresh out of the box, it's not necessarily a magnet
Okay.
because all of those domains are jumbled up.
It has the potential to be a magnet,
It has a potential.
but it needs a little push.
Right. It needs a little push from an external magnetic field.
So how does that work?
So when you apply an external magnetic field, the domains that are already aligned with that field start to grow,
Okay.
kind of like swallowing up their neighbors.
Oh, wow.
And the domains that are pointing in other directions, they start to shrink.
So the external field is kind of like organizing the domains,
Exactly.
forcing them to work together.
Right. And as you increase the strength of that external field, more and more domains fall in line, aligning themselves with the field,
Got it.
creating a stronger and stronger overall magnetization in the material.
So the notes represent this relationship with something called a hysteresis curve,
Yeah.
which plots the total magnetization of the material against the applied field.
That's right.
And I remember seeing this like weird loopy curve.
Yeah, it's a weird curve.
What's going on with that?
It's actually a pretty fascinating story.
Okay.
So as you apply a magnetic field, that curve rises steeply
Uh-huh.
as those domains rapidly align.
Okay.
And eventually you reach a point where all of the domains are aligned.
Mm-hmm.
and the material is as magnetized as it can get.
So that's like the peak of the curve.
Yeah, exactly.
Okay.
But here's where it gets interesting.
Okay.
When you start to decrease that external magnetic field, the magnetization doesn't follow the same path back down.
Interesting.
It kind of follows a different curve.
Okay.
Showing that some of those domains remain aligned.
Oh, wow.
Even when the external field is removed.
So even after you take away the external magnet,
right,
some of those tiny domains stay in formation?
They do. They like to hold on to that alignment.
And that's how you get a permanent magnet.
That's exactly how you get a permanent magnet.
Yeah.
And the amount of magnetization that's left behind after you remove that external field is called remanence.
Okay.
And the width of that entire hysteresis loop tells us a lot about the properties of different magnetic materials.
Okay, I'm hooked. Tell me, what does the width of the loop tell us?
Okay, so the width of the loop can tell us whether a material is going to be a good electromagnet or a good permanent magnet.
Oh, really?
Yeah, so a narrow loop means the material is really easily magnetized and demagnetized.
Okay.
Which is perfect for things like electromagnets.
Got it.
But then a wide loop means that it's really good at holding onto its magnetization. So it's ideal for permanent magnets.
That's so cool. So you can just look at that curve.
That's right.
And know, like, what it would be good for.
Yeah, exactly.
Yeah.
It all comes down to, like, how easily we can manipulate those magnetic domains within the material.
Oh, my gosh.
It's pretty cool.
Mind officially blown.
Good. I like it.
So the notes bring us back to that example of a simple fridge magnet.
Right.
And even with no external field, a massive number of those tiny magnetic dipoles are still lined up.
That's right.
And that's what's creating that magnetic field.
Exactly. And in fact, the notes calculated that to create a magnetic field that strong, you would need a current of 16,000 amps.
What?
Flowing around the circumference of the magnet.
16,000 amps.
16,000 amps.
Just from those tiny atomic magnets.
That's right. All those tiny magnets holding hands.
That is insane.
It really illustrates just how much power is hidden within even like the most unassuming magnet.
Okay, we've covered a lot of ground here.
We have.
We've gone from moving electrons to tiny atomic magnets. And we've even touched on how these principles are applied in MRI machines.
Right.
My brain is full.
I know it's a lot to process.
Yeah.
But this is really just the tip of the iceberg.
I was going to say there's so much more to learn about this fascinating force of nature.
For sure.
All right, we need to take a break.
Yeah, let's take a break and come back and dive a little deeper. So it really is amazing how something so small, like those tiny little atomic magnets, can create such a powerful effect when they all work together.
Yeah. And speaking of powerful effects, let's talk more about those MRI machines.
All right.
I want to know how they actually work.
Okay, so let's zoom back out from the microscopic world of atoms.
Okay.
And look at how we can harness these magnetic principles in an MRI machine.
Okay.
So at the heart of it all is a large cylindrical solenoid.
Right, and that's wrapped in wire, right?
It is, and that wire is usually made of a superconducting material.
Okay.
And this allows it to carry a massive amount of electrical current with zero resistance.
So wow.
Which is key for generating those ultra-strong and stable magnetic fields that you need for an MRI.
Yeah, and they're super strong.
They are.
Like 3 to 5 Tesla.
That's right.
Which is way stronger than even the most powerful fridge magnet.
Yeah, you're absolutely right.
So to put that in perspective, how strong is the Earth's magnetic field?
So the Earth's magnetic field is only about 0.00005 Tesla.
So it's tens of thousands of times stronger.
Exactly. It's a huge difference.
Okay, so the machine's creating this incredibly strong magnetic field.
Yes.
But how does that actually create an image?
Okay, so it targets the hydrogen nuclei in your body.
The hydrogen.
Yes, so hydrogen nuclei are abundant in water and fat molecules.
Okay, so it's basically targeting all the water in my body.
That's a good way to think about it, yeah.
But I still don't see how that creates an image.
So remember how we talked about those magnetic dipoles aligning themselves with an external magnetic field?
Right.
The same thing happens here.
So all the little hydrogen atoms in my body are lining up with this big magnetic field.
Not all of them.
Not all of them.
So the alignment isn't perfect.
Okay.
Some of them align parallel to the field, which is a lower energy state. And others align in the opposite direction, anti-parallel.
Okay.
Which is a higher energy state.
So there's 2 options.
Yeah, 2 options.
Okay.
But the important thing is that there's a slight imbalance.
Okay.
So a few more nuclei end up in that lower energy state.
Okay, so we have this slight majority.
Yes.
Okay, but how does that help us see anything?
So this is where things get really interesting.
Okay.
The MRI machine then sends a pulse of radio waves
Okay.
at a specific frequency
Mm-hmm.
that's tuned to match the energy difference
Okay.
between those two alignment states.
Okay.
And when the hydrogen nuclei absorb this energy,
Uh-huh.
they flip their alignment,
Oh.
jumping up to that higher energy state.
So it's like the radio waves are giving those tiny nuclei a little push?
Exactly. They're getting a little push. And then when that radio wave pulse is turned off, those excited nuclei relaxed back down.
Okay.
They're their lower energy state,
Mm.
releasing energy in the form of radio waves,
Okay.
which are then picked up by detectors in the MRI machine.
So it sends out the pulse,
Yes.
flips them,
Yes,
and then listens for the signal coming back.
exactly. That's a great way to think about it.
Wow.
And by carefully analyzing the timing and the strength of those signals,
Okay.
the MRI machine can figure out where all of those hydrogen atoms are concentrated,
Gotcha.
how dense they are in different tissues.
And that creates the image.
That's how it creates those amazingly detailed images
That's wild.
of your organs and your muscles, your bones, even your blood vessels.
So it's not just about creating that strong magnetic field.
It's not.
It's about precisely controlling those radio waves.
That's right.
And then interpreting the signals that come back.
Exactly. It's a complex interplay of a bunch of different physics principles working together.
And then don't forget about those gradient coils.
Oh, yes, the gradient coils.
Yeah, the ones responsible for all that noise.
Right, all that banging and clanging.
Yeah.
So those gradient coils play a really crucial role in spatial encoding,
Okay.
which is how the MRI machine figures out exactly where each signal is coming from.
Okay.
So they subtly change the magnetic field strength across different parts of your body,
Oh, wow.
essentially dividing your body into this 3D grid.
So they're creating a map.
Yeah, they're creating a map.
Okay.
And this allows the machine to pinpoint the origin of each radio wave echo.
And that's why they have to rapidly switch on and off.
That's right. That's what creates all that noise.
Wow, my brain hurts.
I know.
Just thinking about it.
It's complicated.
Yeah.
But it's really remarkable.
It is remarkable how much technology and physics
Yes.
goes into creating those images.
Yeah. They really are a testament to human ingenuity.
Okay, so we've explored how moving electrons create magnetic fields.
Yes.
We've talked about those tiny atomic magnets
Yeah.
and how they align. And now we've seen how all of that comes together in an MRI machine.
Right.
What else is there?
So now that we've kind of covered the basics, let's dive a little deeper
Okay.
into the world of ferromagnetism.
All right.
So remember those domains we talked about earlier?
Yeah, those little magnetic kingdoms.
Right, where all the atoms are aligned?
Yeah.
So it turns out they're not as static as we might think.
Oh, really?
Yeah, they can actually be influenced by things like temperature
Right.
and mechanical stress.
So, like if I heat up a magnet or I bend it, I can change its magnetic properties.
That's exactly right.
What magnets aren't as permanent as I thought?
Yeah, they're these dynamic systems
Okay.
that are always responding to their environment.
Okay.
So, for example, if you increase the temperature of a ferromagnetic material,
Mm-hmm.
the thermal energy starts to disrupt the alignment of those atomic magnets
Within the domain.
within the domain.
Okay.
This causes the domains to shrink.
Oh, wow.
And if you heat it up enough, they can even disappear completely.
So there's a temperature limit
There is.
for how hot a magnet can get
There is.
before it loses its magic.
Right. It's called the Curie temperature.
Oh, okay.
Above that temperature, the material loses its ferromagnetic properties.
Wow.
And it becomes paramagnetic,
Okay.
which means it's only weakly attracted to magnets.
So magnets are more sensitive than I realized.
They are.
What about mechanical stress?
So if you hammer on a magnet
Uh-huh.
or bend it,
Okay.
you're essentially just jostling those tiny magnetic domains.
Okay.
And this can disrupt their alignment
Uh-huh.
and even
Okay.
change the overall magnetization of the material.
Even just dropping a magnet could potentially weaken it.
It's possible.
Yeah. Mhm.
And so understanding how these environmental factors
Right.
affect magnetic properties is really crucial
Okay.
for designing new magnetic materials
Uh-huh.
and optimizing their performance for different applications.
This is all so fascinating.
It is.
It's amazing how much depth there is to something as seemingly simple as a magnet.
I know we've only just scratched the surface.
Yeah, I was gonna say,
There's so much more.
so much more to learn.
Yeah, there's a whole world of research and development happening
Okay.
in magnetism,
Mm-hmm.
from like creating new materials for data storage to building super powerful magnets for energy generation
That's crazy.
and even developing new medical therapies.
Wow. So what are some of the most exciting areas of research in magnetism right now?
Okay, well, there's so many different avenues being explored.
Yeah.
But like one example is scientists are working on developing new types of magnets
Okay.
that are even stronger
Uh-huh.
and more efficient than the ones we use today.
Okay.
So imagine the impact that could have on things like electric motors,
Yeah.
wind turbines,
Wow.
countless other technologies.
What about for medical applications?
Yes. So there's a growing field called magnetic hyperthermia,
Oh.
which uses magnetic nanoparticles to target and destroy cancer cells.
Oh, wow.
So imagine injecting tiny magnetic particles directly into a tumor and then using an external magnetic field to heat those particles up.
So you're like cooking the cancer cells?
Yeah, you're basically cooking the cancer cells from the inside out.
That's insane.
It's pretty amazing.
What else?
So researchers are also exploring using magnetic fields to stimulate nerve activity
Wow.
and potentially treat neurological disorders like Parkinson's disease.
Wow.
And there are even studies looking at how magnetic fields can promote bone healing
That's incredible.
and tissue regeneration.
So many applications.
So many applications. And with every new discovery, we're gaining a deeper understanding of this fundamental force of nature and how it can really shape the future of technology and healthcare.
You know, I could talk about magnets for hours.
Me too.
This is so cool.
There's always something new to learn and discover.
But unfortunately, we are running out of time for this deep dive.
Okay.
But before we wrap up,
Yeah.
I want to know if someone wants to learn more about magnetism.
Yeah.
Where should they start?
Okay, so there are tons of great books and websites that explore the wonders of magnetism.
Okay.
So if you're looking for a classic textbook that explains things really clearly and thoroughly, I would recommend Electricity and Magnetism by Purcell and Morin.
Okay. And what if I want something a little more accessible?
So the Hyperphysics website, hosted by Georgia State University, has a fantastic section on magnetism.
Perfect.
That's really informative and engaging, even if you're not a physics expert.
Awesome.
And then if you want to kind of dive into the latest research, the journal Nature Materials frequently publishes cutting-edge articles
Perfect.
about magnetism and its applications.
We'll be sure to include links to all of that in the show notes.
Awesome.
Okay, well, I think that about wraps it up for this deep dive.
Yeah.
Thanks for joining us on this magnetic adventure. All right, so welcome back to the deep dive. We've been talking all about magnets.
Magnets are so cool.
They are so cool. We've learned so much about like how they work.
Right, like starting from those basic connections between electricity and magnetism to how those magnetic domains behave in ferromagnetic materials.
Yes, and before we wrap up this episode, I want to go back to something that really stuck with me.
Okay.
Remember how even just a simple fridge magnet can have like thousands of amps of current flowing around it?
Yeah, all thanks to those tiny little atomic magnets.
That are all aligned?
Yeah. It's a perfect example of how like this collective behavior at the atomic level can really create huge effects that we see.
It's kind of mind-blowing.
It's counterintuitive to think that something so small could be so powerful.
Right. Like you think about those tiny atomic magnets.
Right. But when you have billions and billions of them, all pointing in the same direction, their combined force is incredible.
So what if we could control them?
Oh, man.
Like even more precisely.
That's the dream.
What could we do?
The possibilities are endless.
Right.
Yeah, like imagine being able to manipulate individual magnetic domains to store information. Okay. At the atomic level.
Wow.
We could create data storage devices that are way beyond anything we have today.
Like how much storage are we talking?
I mean, we could be talking about storing like the entire Library of Congress.
Wow.
On something the size of a sugar cube.
That is wild.
And that's just one application.
Real, what else could we do?
Imagine developing magnetic sensors with like incredible sensitivity. That could detect tiny changes in the environment. Or even in like biological processes within the human body.
So we could like revolutionize healthcare.
Exactly. We could revolutionize healthcare, environmental monitoring.
Wow.
All sorts of things.
It feels like we're just getting started.
Yeah, we really are at the tip of the iceberg.
With magnetism?
With magnetism. And as our understanding of the quantum world keeps growing. Who knows what other amazing properties of magnetism we'll discover.
Yeah, like there could be applications that we haven't even thought of yet.
Exactly. Things we can only dream of right now.
That's what's so exciting about science.
It's the endless frontier.
Yeah, there's always something new to explore, always deeper mysteries to unravel.
Always.
Okay, well, I think this deep dive has given everyone a lot to think about.
Hopefully it sparks some curiosity.
Yeah, from those basic principles of electromagnetism
Mm.
to the crazy possibilities of future magnetic technologies.
It's been a wild ride.
It really has. So, until next time, keep exploring, keep asking questions, and never stop learning.
That's the key.
Thanks for joining us on the deep dive.